you very much for having me, to the NeurIPS organizers for the invitation, and also to the host for the introduction, the technique. Yeah, as was said, today's talk is going to be on discrete curvature and applications in graph machine. So just to give you an idea of the kinds of problems that we see in graph machine learning, just a heads up, the talk will be mostly focusing on theory and on algorithms, not so much on particular applications, but graph machine learning is very broadly applicable, and the kinds of tools that you see in this talk can really be applied in a variety of different scientific areas and also for data science. So what you see here on the slide are three very classical tasks we encounter in graph machine learning. For instance, we start at the top graph classification. So here you could think of a task like having a set of molecules given, each of which have a chemical structure that we can represent as a graph. And then our task is to solve a classification task on this problem. So we want to identify labels for each graph according to maybe some chemical properties such as acidity, or perhaps how effective these molecules are in a graph. So that would be an instance where our input is a set of graphs, and we want to assign labels to one label to each graph. We can also solve classification tasks on the node level. So in that case, our input is just a single graph, and we want to assign labels to different nodes in the network. So a classical example of this, perhaps if we are analyzing social networks, and maybe we want to identify which nodes correspond to actual human users and which ones are bots. And then to give you a third example of link prediction, so for instance, in drug discovery, yeah. Is that better? Is that better? For the people online, can you hear?
Yes, yes.
Yes? Okay. Yes, so the third task is an example of link prediction. So here, imagine that each node in the graph represents a drug, and then we have an edge between the two nodes if there's an adverse reaction. And maybe from experimental data, we know a few adverse reactions, but perhaps not all. And we want to use our data to infer additional links, additional edges, so additional adverse reactions. So those would be three classical tasks that we can keep in the back of our mind as we go through different algorithms. And then, as the title of the talk already says, the key sort of mathematical tool that we will see throughout the talk is curvature. And so curvature is, of course, a very central concept in differential geometry. Even if you don't have a background in differential geometry or haven't studied it in particular detail, you probably have some intuition on what curvature means. So here at the top, you see three different manifolds or surfaces. So for instance, the Euclidean plane that you see, here. That's a classical example of a flat space, so a space that has curvature 0. And then we have a sphere. A sphere is a classical example of a space that has positive curvature. And then you might have also seen those like saddle-like structures that would be a classical example of negative curvature. Right, so just those classical ideas and intuition about curvature we usually associate with continuous spaces, and this is also where curvature was sort of initially studied. Now in graph machine learning, we have discrete data structures, so usually graphs, but maybe also hypergraphs or simplicial complexes, maybe even just sets or point clouds. So we have discrete data. Right? So in order to use notions of curvature in that space, we have to think carefully about how to define curvatures in such settings. If you know a little bit about sort of mathematically how curvature is defined, you know that it's very essential to have a differential structure to define curvatures. And of course, in discrete spaces, we don't have a differential structure, so we have to work around that. And one way to do this is via curvature analogy. So in the first part of the talk, we will look into exactly this. How can we use curvature analogies to define discrete notions of curvature that we can then apply to discrete data structures such as graphs. And then once we have defined those notions of curvature, we want to use that to look into graph machine learning algorithms that leverage such curvature characterizations of the geometry of our input data. And I want to just give you a very brief idea of how those algorithms look like, and then we will focus on specific parts in the second and third part. So a classical class of algorithms where curvature has been used for quite a while are shallow graph machine learning methods. So the canonical task or example here is community detection. So community detection is an unsupervised task. So here we're given single input graph, and we want to identify densely connected substructures in the graph. So for instance, in the example that you see here, we have three subgraphs that are much more densely connected than the connections between them. Right? So in a setting like this, we use this sort of topological information to identify clusters in the data. And then usually we make a homophily assumption. So we assume that if two nodes share a lot of neighbors, are very densely connected, then usually they're similar, right? So this is how we would identify clusters, hopefully similar nodes in the graph. There are also versions of this which are a bit more realistic, where the situation looks more like this, right? Where we don't have such a nice separation, but we have sort of overlapping clusters. Maybe the clusters share several nodes in between them. And that's actually for classical community detection a very challenging setting. It turns out that the geometric characterization that curvature gives us of the graph is really useful for identifying such community structure. Namely, we will shortly see that those edges that go in between communities have a particularly negative curvature. And then in between those communities, we have a particularly high curvature. So curvature, in a sense, captures, among other things, something about the density in particular regions of the graph. So as long as we can relatively efficiently compute the curvature, we can use that to infer a lot about the structure, which we can then use in simple supervised downstream. And then something like this, in this case, we can also use curvature. So there, this is the first paper that's listed here that has looked into how to still use curvature in this setting by looking at the dual of the graph. So there are lots of nice extensions that one can do, even in settings where it's not so sort of obvious on where to find the sparse connections and the separations between the clusters. A second class of applications, and that's one where we will have a closer look in this talk, are graph neural networks. So architectures for performing deep learning on graphs. Those are very popular. And in fact, for the three tasks that we saw initially, graph neural networks are, in most cases, the state of the art. And most graph neural networks architectures rely on message passing. And while in generally message passing works quite well, there are some crucial shortcomings that arise, oftentimes connected to the topological structure of the graph. And we want to look at two effects. One is limited representational power, so limitations in are the kinds of functions that a graph neural network can learn. And then also so-called over-smoothing and over-clumping effects. Those are topological effects that inhibit the graph neural network from learning good representation. And in both cases, we can use geometric characterizations via curvature to mitigate those two shortcomings. And that's what we'll focus on in the second part of the talk. And then in the third part, we will look into sort of zooming out what discrete curvature can tell us about the geometry of data, and in particular, how we can use discrete notions of curvature to understand something about the manifold from which our data set, our sample might come from, and discuss what connections those kind of insights can have regarding learnability of algorithms and also regarding implications for representation. So that will be the third part of the talk. So in the first part, just looking at notions of discrete curvature so that we understand how to actually compute this, and then looking at implications for graph neural networks, and looking at how we can use those notions to characterize the geometry of data. So let me start with notions of curvature. So we discussed this already a little bit, right? We have some intuition on what curvature means from the continuous setting, from low-dimensional surfaces that we have encountered. Classically, curvature is defined like this, the equation that you see here, the curvature tensor. In general, it's very difficult to compute the full curvature tensor on any data or in any discrete setting. Again, that has to do with the lack of a differential structure in those settings. In what we do in the context of discrete curvatures is that we focus on one particular kind of curvature, sort of one piece of this full curvature tensor, namely Ricci curvature. And instead of sort of deriving a complete analogy of the classical curvature, we will use curvature analogy. So basically, we will take the perspective that in the continuous setting, curvature characterizes certain properties or has certain relations with other classical geometric characteristics. And maybe those properties or those classical characteristics have a well-studied analog in the discrete setting. So we could try to find a notion of discrete curvature that preserves those relationships. Maybe it doesn't preserve all the relationships and all the nice properties that classical curvature has, but at least some of those properties. And as long as we choose a curvature notion in practice that preserves the properties that we want or characterizes the relationships that we are interested in, then we are good. So that's the idea of curvature analogies, and you will shortly see examples of what I mean by that. So again, just to say upfront here, we're not trying to characterize the full curvature tensor in the discrete setting. That I think is, from what we know so far, not feasible. And we want to focus on just Ricci curvature. Ricci curvature is an intrinsic local curvature. And basically what it measures is sort of shown here in this picture. We look at the point on the manifold, and then we look at the so-called geodesic dispersion. So we look at the geodesic ball at that point, and then depending on the curvature of the manifold, that tells us something about sort of how far geodesics that start at that point would diverge. So this is one characterization that we can get from curvature. Again, it's not the full curvature tensor. It can't tell us much about the global geometry. It's a very localized curvature measure, but it turns out that that is a good measure to consider in the Ricci setting. So how do we define a discrete analog of Ricci curvature? So the first notion that we will see in this talk, I should say we will only see two notions in this talk. This is by no means an exhaustive list, just a sort of biased selection of the two curvature notions that I have studied most, but there are other notions out there. The first one that we will see is Olivier's Ricci curvature. So here, the analogy, the curvature analogy that is built is between the behavior, the relationship of curvature and the behavior of random walks on a manifold. So if we're in a continuous setting and we start two random walks at nearby points, then the trajectories of those random walks will draw together or stay nearby with high probability if the manifold has locally positive Ricci curvature, and they will draw apart fast with high probability if the manifold has negative Ricci curvature. Now, random walks is something that we can easily study in the discrete setting, right? Suppose we're in a setting like this cartoon here, and let's say we wanted to understand something about the curvature of this red edge. We can look at sort of nearby points, nodes U and V, right? And then we can start a random walk on both of those nodes. Let's say we look at uniform random walks, so that jump with probability 1 over to the degree to each of the neighbors, right? This is a sort of a notion of random walk that's easy to study in the discrete setting. And then we want to measure sort of the behavior of the trajectories that those random walks introduce by looking at the measures that they induce, right? And then the sort of whether those random walks are likely to stay nearby or draw apart, we can measure with the Wasserstein-1 distance between those two measures. So essentially, we solve an optimal transport problem, right? And then we see that if those two nodes have a lot of joint neighbors, So a lot of triangles are adjacent to that edge. Here we just have one, but maybe we have in densely connected regions of the graph many such joint neighbors. And then that sort of introduces shortcuts in the optimal transport plan. So we will get a relatively low Wasserstein-1 distance. And then if the two nodes don't share a lot of neighbors and have a lot of sort of the neighborhoods are not overlapping a lot, then the Wasserstein-1 distance between those two measures will be relatively large. So if we plug that knowledge in here, right, we look the Wasserstein-1 distance between those measures over the path distance between the two nodes. In that case, that's just 1 because we have adjacent vertices. So if we do 1 minus that ratio, then we get a negative curvature whenever we have high transport distance. And that's exactly in the case where the two nodes don't have a lot of shared neighbors. So it's very unlikely that the random walk jumps from one neighborhood to the other and stays nearby. But we will get a positive curvature if the Wasserstein-1 distance is small. And that means the two nodes are sort of exploring both of the joint neighborhoods at the same time. Right? So we get a similar sort of curvature characterization that we would expect in the analogous continuous case. So that is one curvature analogy and one notion of curvature that we will see throughout the talk. The second one is slightly less intuitive, but still very valuable for applications in practice. And that is Fuhrmann's curvature. In Fuhrmann's curvature, the curvature analogy that we're using is the so-called Bochner-Weizenberg identity. This is what you see here in the first box. So that's a classical identity, a classical relationship between Ricci curvature and the Laplacian in the continuous setting. So this is a well-known identity in differential geometry. And then Fuhrmann proposed a combinatorial equivalent of this that you see in the second box. This was originally introduced on CW complexes, which is a very general class of discrete structures. But if you look at graphs as a special case of CW complexes, or simplicial complexes would also be a special case, for instance, and then you can specialize that to the graph case, which is what we will be doing. And here in the discrete Bochner-Weizenberg identity, you kind of get the same thing. So you have Laplacians showing up. Laplacians in the discrete setting are, of course, very well studied, right? In the graph case, the graph Laplacian, and we know that very well, and its properties have been very well studied. And then Fuhrmann said to just define a notion of Ricci curvature that is consistent with that Laplacian and that preserves this fundamental relationship that we have in the continuous setting. If we specialize that to the graph case, we get that kind of notion of Ricci curvature again for this red edge. Right? This is the analogous graph to what we had before. And then you see here, this notion sort of aggregates a lot of combinatorial information in the neighborhood of that edge. So for instance, we see the degrees of the two vertices. We also see what sort of higher order relationships exist between the two nodes. So for instance, here you see a triangle count, right, and a quadrangle count. And then one could look at higher order cycles as well. So in this case here, for instance, we would count the degrees of the vertices and then also the presence of this triangle here into the notion. Okay, so just to compare those two notions, so we have Olivier's Ricci curvature. Here, the curvature analogy derives from the behavior of random walks and optimal transport and its relation to Ricci curvature, and Fuhrmann curvature, where the curvature analogy is related to relationships between curvature and the Laplacian. I should say that for Olivier's Ricci curvature, there's a very rich theory. So in the discrete differential geometry literature, that's been very well studied. Fuhrmann curvature, not so much. I think there's still quite a bit to do there. From a computational perspective, that's something we should keep in mind as we look into applications. If you recall, when we introduced Olivier's curvature, we said we have to compute the Wasserstein-1 distance. Right? So we have to solve an optimal transport problem, and that can be expensive. At least if we solve it exactly, there are approximations of this using, for instance, synchron distances, which is an approximation of the Wasserstein-1 distance. There are also ways of deriving a combinatorial approximation. a combinatorial approximation of Olivier's curvature that we've since recently derived that is even faster than this. So there are ways of speeding this up. Fuhrman's curvature just by construction is much more efficient, right? If you remember that simple equation that we had written on the previous slide, this is essentially just an aggregate of combinatorial information, decrease number of cycles. So that is naturally much, much faster to compute. Those two notions, even though they derive from different curvature analogies, are very closely related. One can see this empirically if you compute the curvature of two graphs, both curvatures of graphs, and compare them. It's very highly correlated. In particular, regions that have low versus high curvature have that in terms of both curvature notions. And one can also establish formal theoretical between the two. Yeah.
Can you make a comment on when you would want to use one notion versus the other?
Yes, that's a good question. So usually it's a computational matter. So it's not always possible to compute the exact Olivier curvature, especially if you have a very large, very dense graph that becomes computationally infeasible at some point. In that case, you want to use Fuhrman curvature or like the combinatorial approximation. Yeah, so this is sort of in favor of Fuhrman's curvature. But yeah, if you sort of need a good theory, or later on when we will talk about learning something about the geometry of data, there is actually a lot of relationships that have only been proven for Olivier's curvature. So there you would have to use that. Yeah, but it's a good question. I think in practice there's not always a sort of definite answer to that. It would depend on maybe trying out both and seeing which one gives you a better. Okay, so we have two curvature notions. Now let's talk about what we can do with them. Yes, so we want to talk about applications of curvature in graph neural networks. So let me just remind you what graph neural networks are, or the main paradigm between most of the graph neural networks that are currently being used, namely message passing graph network. Apologies to those who have seen this before. So message passing is a very simple iterative procedure, but that turns out to be very powerful for learning with graph structured data. In the message passing graph neural network, each layer consists of an aggregation and an update function. So if we start with the aggregation function, so typically when we use graph neural networks, we have attributed graphs. And what we want to learn is an embedding of the nodes that captures both connectivity structure, so the adjacency, the edges of the graph, and also information that's given on the node. So a good initialization, usually if we have an attributed graph, is to initialize those node embeddings with the attributes in the input graph. That's usually a good initialization. And then in each layer, what we do is that we aggregate the attributes. So we learn an embedding for each node, right? And let's think about how we iteratively update the representation of that node. So we look at all its neighbors. We aggregate that information into a multiset. So this is just all the representations, so all the attributes at that time. And then we pass that through an aggregation. And here we have some choice on how we choose that aggregation function. We could take like an entry-wise average. We could take like a max. So we compute some sort of summary statistic. And what we get from this aggregation is the so-called message. And then in the second piece of this, the update function, we take the message and the current representation of that node. And then we pass that through an update function. Oftentimes that's an MLP. But again, we have some choice. So it should be some trainable function. And then that outputs a new representation of the node. So due to this construction, you see that in layer 1, we capture information from the direct neighbors of our node. In layer 2, from the 2-hop neighborhood. In layer 3, from the 3-hop neighborhood, and so forth, right? So we iteratively capture information from further and further away nodes. So that's the essential idea. So in general, this works really well, and that's a very popular architecture. Has been used very widely, but it's not without its challenges. Two challenges that have received a lot of attention recently are oversmoothing and oversquashing. Oversmoothing usually appears is a problem in regions of the graph that are very densely. Right? So let's say if we look at the region here with the red edges, and you look at a node and maybe it's 1-hop and 2-hop neighbors, they share a lot of the common nodes, right? There's a lot of overlap between the neighborhoods. So if you think about how we aggregate information in the aggregation step during message passing, is that we compute an average over the 1-hop neighborhood and then the 2-hop neighborhood and so forth, right? And if the nodes share a lot of the same information, then we sort of keep averaging or keep computing summary statistics of essentially the same content. And that means that after a couple of iterations, we are starting to lose information. We just have averages of averages, and we're starting to lose information. So after a couple of layers, if we're in a very densely connected region, all the node embeddings will start to look very, very similar. And any sort of initial differences that were, for instance, in the node attributes at input gets lost at that point, right? And that can be very challenging if, like in the downstream task, we rely on capturing that information. So that's something that occurs in densely connected regions and as the network gets deeper. The sort of opposite effect to that is oversquashing. In that cartoon here, we would expect that along the blue edge, right? So imagine we were to update the representation of this node, right? Then at this node here, we're always averaging over the neighborhood that is largely determined from over here. And then this node only ever sees a statistic, an aggregation of the information captured over here. So in particular, any nodes that are sort of further away from this node in this part of the graph, we will only ever see a very, very aggregated, diluted amount of information, right? So if we have a downstream task that depends on capturing well long-range information in the graph, then this way of updating information makes it so that our node representations do not capture that very well. And that occurs at kind of like bottlenecks in the graph, right? In this case here, this blue edge is sort of like a bottleneck or like a narrow path in the. So those two effects have been well studied from just like purely this perspective that I just explained now. But we can also use curvature and geometric characterizations of the structure of the graph to analyze those two effects or to say something about where those effects might occur. So in particular, if you think about, let's say, we only do this for Olivier curvature, where it's sort of easy to see, right? In the red region, where we would expect over smoothing, there we have a very densely connected graph, and the two nodes share a lot of common neighbors. So over smoothing coincides with where we have high curvature, right? And then this bottleneck where we would expect over squashing to occur, that's a region in the graph where we have particularly low. So this is just saying this heuristically. For Olivier curvature, we can show the same with Foreman curvature and also with other curvatures. So this is a sort of a general insight into if we have a meaningful curvature, they should give us that characterization. So how can we now use those insights? One way of mitigating oversmoothing and oversquashing effects that's been used a lot in the literature is via rewiring. So rewiring is a pre-processing technique that makes small edge perturbations to the input graph before we actually start the message. So we're basically in a hopefully smart way changing some of the edges. Maybe we add some edges, we remove some edges so that the topology of a graph changes sufficiently to where we have less oversmoothing and less oversquashing. But we want to do this only to a very small amount, right? Because we don't want to lose any of the critical information. So curvature can be used to guide those rewiring approaches. In terms of edge perturbations, so to mitigate oversmoothing, right, we want to make those very dense regions less dense. So we need to remove some edges where we have oversmoothing. and we want to add some edges where we have over squashing to kind of widen the bottleneck. This is nice to see here in this cartoon. Right here, a few edges have been added, and that sort of widens the. It turns out that curvature can really give us good insight into sort of what is the right amount of edges to add and edges to remove. We can sort of see this a little bit in the curvature distribution here. So this is for the case of Foreman curvature, but it would look very similar for Olivier's curvature. Right? So here we have a distribution of curvature. We have one sort of set of edges that has very negative curvature. This would be those edges that go in between the densely connected regions. And then we have a second set of edges that has a much higher curvature. And this distribution, or the curvature, we can characterize with a so-called curvature gap. So that's a characteristic that tells us basically how far these two are apart. So that kind of distribution is something that we see very often in real-world graphs, at least in graphs that have a community structure, and then sort of how strong that community structure or that separation into different communities with sparse edges in between, how strong that is something that we can characterize with the curvature gap. And that tells us something how wide these far apart. And then we can use that from that characterization, we can derive sort of upper and lower bounds on what is sort of too high curvature and what is too low curvature. And then we can go into the rewiring and just say for all edges that are below the threshold, so that I have too negative curvature, in this case, that would be this one edge. We add some parallel edges, so we connect some of the neighbors of those two adjacent nodes to widen the bottleneck. And then we look at all the edges that have too high curvature, and we remove those, right, that are above our curvature. So that's a very simple idea. Why that can mitigate over smoothing and over squashing, one can also show mathematically. I won't be able to show this in the graph, but one can in the talk. But one can get sort of nice bounds on how curvature influences those sort of converging behavior of the node representations. And what I want to show you are just a few results on what we can get from this pre-processing routine. So this is for a graph classification case. So remember, this was one of the examples where our input was a set of graphs, each of which represent the chemical structure of a molecule, and we want to label them. And then you see here for a GCN, a graph convolutional network, that's like a classical message passing neural network. And then you see here in the last column, this is the accuracy that the GCN reaches if we don't do any pre-processing. If we do pre-processing with curvature, then those are various different variants that have been proposed. Here's ours with Foreman curvature. And then there's also another variant of this that uses the spectrum of the graph Laplacian to guide rewiring, which in one case does really well, but oftentimes does a little bit worse than curvature. Why do we use Foreman curvature here? So first, we talked earlier about scalability, right? If we have very large graphs, Olivier's curvature might not be feasible to compute, but Foreman curvature basically always is, because it has this simple combinatorial equation. And then it also only uses local information. So we only ever have to look at the two-hop neighborhood of an edge. So we can very easily parallelize the computation of that curvature. So that makes it very feasible for a pre-processing routine. And then, yeah, I mentioned there are also theoretical guarantees that sort of back up why this is expected to work, although I did not have time to discuss here. Okay, so this is over-smoothing and over-squashing, which is often cited as one sort of shortcoming of message passing graph neural networks. The other big one is limited representational power. Namely, it turns out that there are certain classes of graph-structured functions that a message passing graph neural network cannot learn. Unfortunately, even quite simple ones that could really impact sort of the downstream performance of those kinds of architectures in practice. So a way to think about this, or to analyze what representational power means, is to look at the following question. So a GNN, as we discussed, learns a representation of the graph, right? And then we can ask, if we give it two graphs, will it learn the same representation if and only if those two are topologically not identical. So if they're very, very similar, but not quite topologically identical, would the graph neural network be able to tell those two apart, or would it learn the same representation? And that means that, like in a downstream task, it wouldn't be able to distinguish between those two. So topologically identical here means, let's say we have two graphs, G1 and G2. They have an adjacency matrix, or adjacency matrices A1 and A2, right? This is the edges, the connectivity structure of the graph. And then they have node attributes X1 and X2. And then basically, if we were to permute the adjacency matrices and the node attributes in some way so that we could map one graph to the other, and then those two would be topologically identical, right? They would be identical up to permutation. Graphs are fundamentally permutation invariant, right? So there's no natural order on the nodes. There's no natural way to say this is the first node and the second node and so forth. So graphs are permutation invariant. And whenever we have two graphs that are up to permutation exactly the same, then we should treat them as being the same, right? As being topologically identical. So this underlying problem of deciding whether two graphs are identical or not has been studied for a long time as graph isomorphism testing. And that's known to be computationally extremely difficult. In fact, it's no known efficient algorithm. We have no known efficient algorithm for this problem. But we have some quite good heuristics. One of those heuristics is the Weisfeiler-Lehmann test. I won't be able to go in detail over the Weisfeiler-Lehmann test, but essentially what the Weisfeiler-Lehmann test is doing is very, very similar to message passing. In particular, those aggregation of the neighborhood information that we saw earlier. There's a step in the Weisfeiler-Lehmann test that very, very closely resembles that. And in fact, one can show that any two graphs that the Weisfeiler-Lehmann test could distinguish can also be distinguished by a graph neural network. And also, if two graphs that are not topologically identical cannot be distinguished by the Weisfeiler-Lehmann test, then a graph neural network can also not do that, right? So the Weisfeiler-Lehmann test is a really good proxy for which kinds of functions message passing graph neural networks can. To give you some examples, so what you see here in the first row, G1 and G2 are obviously topologically not identical, right? We can tell that right away. G2 is disconnected, G1 is connected. If we look at, for instance, the largest cycle in G1 is 6, and G2 it's only 3, right? So clearly those two are not topologically identical, but message passing graph neural networks would learn exactly the same representation for those two graphs, so they would not be able to distinguish those graphs. That then also means that functions like what's the diameter of a graph, what's the largest cycle of a graph, is a graph connected? Those are functions that a message passing graph neural network could not reliably learn. Right? Now you might notice that those two are regular graphs. And when do we encounter regular graphs in practice? So one might think it's not that bad of a limitation. But unfortunately, they're also not regular graphs that are not topologically identical and that still a message passing graph neural network could not distinguish. So here's a classical example, for instance, of two chemical structures. And the message passing graph neural network would learn exactly the same representation, right? So if you think back to these biochemistry tests, drug discovery tests that we discussed earlier, that could be a real problem, right? If it's not able to distinguish between chemical structures like this. So what can we do about it? Yeah, so here's this result. So this is a landmark paper in graph machine learning, or two that came at about the same time by Kru et al. And Morris et al. that showed this connection between the Weisfeiler-Lehmann test and the message passing graph neural networks, and then we're able to characterize the limitations in representational power for message passing graph neural networks. Yeah, so what can we do to widen the class of functions that a message passing graph neural network can reliably learn? There's been a lot of proposals for this. There's been proposals related to let's take higher order structure into account, and that does work quite well and provably extends the set of functions that message passing graph neural networks can learn. Unfortunately, that also makes the message passing much less efficient. So in practice, that's not always practical. Another proposal is to give the graph neural network access to some structural information that it has a hard time learning on its own. And this is the direction that we want to discuss further here. So there are various different kinds of information that we could give the graph neural network, right? We already discussed a few things that it has trouble with, like for instance, the largest cycle or the number of cycles in the network, right? That's substructures like this. It has a hard time characterizing. So we could, for instance, use substructure, right? We could also think about using classical graph characteristics. So maybe we give it some information about the spectrum of the graph Laplacian. And that, for instance, tells us something about community structure. Whether or not a graph is connected is something that we can see in the spectrum of the graph Laplacian. So this is what you see here, structural and positional encodings are two different types of giving the network access to such informations. And the spectrum of the graph Laplacian would be a classical example of positional encoding. You probably already guess what we are proposing. We're talking about curvature. So can we use curvature characterization to give the graph additional information? So first, I don't have the results here on the slides, but so curvature characterization of a graph is also something that a message passing graph neural network cannot learn on its own, right? One can sort of make this more precise, but even intuitively, we said earlier that curvature looks at this discrete Ricci curvature looks at the two-hop neighborhood of an edge, right? Whereas message passing can only look at a one-hop neighborhood at the same time. Right, so that already gives us a hint that this probably captures something more that classical message passing could not capture. Okay, so how can we give the network access to a curvature characterization? It's a fairly simple fix here. We use so-called curvature profiles. So again, this is a pre-processing routine. So before we even start the message passing, we pre-compute the curvature of all edges in the graph, and then we attach to each node a set of summary statistics. So we want to capture what's in the neighborhood, the minimum curvature and the maximum curvature, and then also some summary statistics such as what's the mean, the standard deviation, or the median. That's what we've written here. It's not very sensitive to what summary statistics we use. It's important to capture the min and the max, and then here we have some choice. It's relatively robust under that choice. Again, if we use a curvature notion such as Foreman's curvature or a combinatorial approximation of Olivier's curvature, we can compute this relatively in a relatively efficient manner, right? And it's usually scalable to large enough graphs to where we can use it in practice. Now, what does that curvature information do for us? So it provably extends the class of functions that the message passing graph neural network can learn. And I want to illustrate that on two sort of toy examples. Of course, those are not graphs that you encounter in practice, but graphs that have been very well studied in combinatorics and in graph theory, namely the Rook and the Chicante graph. In graph theory, they are studied because those are examples of strongly regular graphs. For our purposes here, what we need to know, so both of them have 16 nodes, and all of the nodes have degree 6. Right? Those are regular graphs, so message passing graph neural networks cannot distinguish them, right? So here are plots of the two graphs. And what I have drawn here are essentially the optimal transport plans, right? So if we compare by symmetry, this follows for the other edges, but if we just look at the edge UV that is highlighted in red here, and then the neighborhood of U is shown with these blue edges, and the neighborhood of V with green edges. And then if we want to compute the Olivier curvature of this red edge, right, we would need to, so we place a uniform mass on the neighborhood of U and V, and then we want to map the mass from the neighborhood of U to the neighborhood of V to compute the Wasserstein-1 distance. And then what I have drawn here with those smaller red edges are edges over which in the optimal transport plan, a unit of mass has to be transported, right? And then we see here that we have 3 edges in this graph. And in this graph, we have 5 edges. So clearly, the optimal transport plans are different. So also the curvature profiles are different, right? So if we give the graph access to the curvature information, it is actually able to learn different representations of those 2 graphs. Now, this works with curvature. So one might ask, can we not just achieve that with all kinds of other graph characteristics? And unfortunately, not. So for instance, those 2 graphs have the same spectrum, right? So if we give it positional encodings access to the spectrum of the graph Laplacian, that wouldn't allow us to distinguish those 2 graphs. We also mentioned earlier the substructure counts. So if we give it access to counts of certain substructures, for instance, that could potentially work, but we have to pick the right combinatorial structure. So that requires a lot of fine-tuning and has a very high complexity pre-computing those substructures. So that's not really practical either. LBT is something that looks at the node degree distributions. So clearly here we have uniform node degree everywhere, so that also wouldn't tell us, right? So among those sort of classical types of encodings, really curvature does well here and is fairly scalable. So this was a sort of toy example, but we also see the advantages of that in practice. So here, again, we have a graph classification task, and then also a node classification task. And then you see here in each of those 3 blocks is a different kind of message passing architecture, right? We have, again, the GCNs that we saw earlier, and then 2 other variants. And then in each block, the top row is no encoding, so just pure message passing. And then we have the substructure counts and the spectral encodings, and then like another encoding that's known to work quite well. But we see that the curvature encodings really vastly outperform no encodings and also really substantially outperform the other encodings. So this curvature characterization seems to also in practice capture a lot of important structural information that the network can really use to boost down performance and to learn richer representations that capture more important structural information. Okay, I think I have 10 minutes, so that's great. I can talk some more about the 3rd part, continuum limits of curvature. So here we're gonna look into a slightly different setting where our input is not necessarily sort of given as a graph, but maybe we're just given a point cloud, and we construct a graph that captures the metric information in that point cloud. So what do I mean with this? So suppose we have a data set, here script X, that contains samples from some high-dimensional Euclidean space. And let's say that those samples really lie on some low-dimensional data manifold, but we know nothing about this manifold, right? We only know there's some low-dimensional structure, but we have no idea about the geometry of that low-dimensional structure. So one way to represent the metric information in such a point cloud is to construct a similarity graph by constructing epsilon neighborhoods. So each point in our point cloud becomes a node in the graph, and we draw an edge between 2 nodes whenever they're within an epsilon distance from each other, right? And then we can vary epsilon, and that gives us a family of graphs that capture the sort of metric information, the distances in our point cloud. If we look at such a graph, a natural question in this context is to say, what can we learn from this graph about the geometry of the manifold from which the data was sampled? Right? We can ask this question or we can ask various different sort of variants of this question. First, we can look at asymptotic limits. So if we were to sample more and more data points, right, we get a denser and denser sample that sort of covers more and more closely the manifold. Then we could ask, like, in this continuum limit, do we asymptotically approach the geometry? We measure things like the curvature or maybe the spectrum of the graph Laplacian. Do we learn something about the curvature and the Laplacian of the underlying manifold? We are, of course, particularly interested in curvature, right, in this context here. And for curvature specifically, we can ask two types of questions. We can ask sort of point-wise, can we recover point-wise the local curvature at like a single point on the manifold? And then also, even though curvature, or the Ricci curvature that we're considering here, is a very local measure, can that tell us anything about the global geometry of the manifold? And in particular, in the context of Ricci curvature, what's usually very interesting to know is global bounds on the Ricci curvature. And I will give some examples later on why that is interesting in a machine learning context. But so in this context, the second question that we can ask is, by just having access to this graph, to this point cloud, if you compute the discrete curvature on that graph, can we learn something about global curvature? I should say a word here on geodesic distances, so on measuring distances in that graph. So ideally, if we have samples from a low-dimensional manifold, right? So the right way to measure distances in the data space would be to measure geodesic distance. So for any of those 2 points, what's the distance on the manifold? If we construct a geodesic, the shortest path between 2 points on the manifold, what's the length of that path? Right? That would be the right way to measure distances. Of course, if we know nothing about the manifold and we only have access to those samples given in a high-dimensional Euclidean space, the best we can do is to just measure distances in the ambient space. And those will very likely not completely align with geodesic. So in this context, we consider 2 settings. So the first one is what is usually done in the literature, is to just say, okay, we assume access to an oracle that gives us the geodesic distances. That, of course, is not realistic for geometric data analysis in practice. We will never have access to such an oracle. But let's say we had access to such an oracle, what can we say? And then the second setting is where we actually take into account this impossibility of knowing the true geodesic distances and construct a data-driven approximation. Okay? So those 2 settings we should keep in mind. So going back to those continuum limits. As I said, those have been studied for a while. So in particular, a classical question are geodesic distances. So the question basically that we have just discussed. If we only have access to the graph and we approximate in a data-driven way geodesic distances, maybe by shortest path on the similarity graph, does that in some way in the continuum limit approach the true geodesic distance? And in some cases it's true. So there's a lot of nice work on talking about what characteristics of the manifold make statements like that true. Another classical characteristic that's been studied in this setting is the continuum limits or consistency of the graph Laplacian. So if we take out our similarity graph, we compute the graph Laplacian, does that tell us anything about the spectrum of the Laplace-Beltrami operator? For instance, if you compute the spectrum, is that in some way consistent with the Laplace-Beltrami operator? So there's some nice work on this, for instance, by my co-author on this, Nicolas Garcia-Trios, has done some really nice work on studying that for the graph Laplacian. For the curvature, this problem has really been understudied. There's before our work, there's a single work that I'm aware of that looks at asymptotic limits of Ricci curvature, assuming access to geodesic distances. And importantly, it's an asymptotic result in the continuum limit. So it can't give you error bounds, right? In practice, we don't have infinitely many points. We just have n points. We have the finite point cloud. So ideally, we would want to give error bounds on what kind of accuracy can we get with just n sample points. And that was not something that can be gained from those results. We looked into sort of mitigating those 2. Oh, and this is also, I should say here, this is also only a local, this looks at the local consistency question, so not related to global curvature. So let's look first at the local point-wise consistency. It turns out for Olivier's curvature, we can show such a consistency result. And importantly, we can show this in the less restrictive setting 2, which is what I stated here. One can, of course, also show it in setting 1. Actually simplifies the proof quite a bit. But what you see here is stated in setting 2. And importantly, those are non-asymptotic consistency results, so we can get an actual error bound. Right? So just, I of course won't be able to do the proof here. You can find it in the paper. But just to explain you kind of how this result looks like. So we have the A sub G, that's the Ricci curvature that we can, the discrete Ricci curvature that we can measure on the similarity graph. And then we have the true Ricci curvature at the corresponding point on the manifold. And then we get a sample complexity here, right? N is the size of our point cloud. So we get an error bound in terms of that complexity of that, the size of that sample. And then, of course, it depends on the epsilon radius and also the intrinsic dimension on the manifold. So for the neighborhood radius, I should say another word, if we choose that to be very, very small, then the graph will be largely disconnected. So our geometric graph will not capture a lot of the information that we need. So that's bad. If we make epsilon too large, then the graph is almost completely connected, and that will also destroy some of the geometric information that we want to capture. We have to tune epsilon very carefully, but there are ways of making that principled, like how epsilon should be chosen. The details you can find in the paper, but that's not an unsolvable problem. And then one more thing here. So this is just summarized with beta, the approximation error from the data-driven geodesic distances. So that can also be made more precise depending on the geometry of the underlying manifold. But this is the kind of result that we get. And then we can also show a similar result for the global curvature bounds, right? So suppose that our underlying manifold has bounded Ricci curvature, then we can show that, in fact, the geometric graph will inherit this property with respect to Olivier's Ricci curvature. And we can basically learn that global curvature bound from data. And similarly, we get a non-asymptotic bound, so we get a sample complexity for this. And then we also can say how that depends on the characteristics of the manifold. I'm just summarizing as alpha sub m, and then the intrinsic dimension, for instance, the neighborhood radius, and so forth. Okay, so why is this interesting? Sort of aside from discrete differential geometry, right? Understanding these consistency results and continuum limits is, of course, sort of from a theoretical perspective, a very interesting problem to look at. But in the machine learning context, what can we get from this? So in the context of representation learning, that's a very well-studied and established field within machine learning, within geometric data analysis. Right there you see techniques such as manifold learning, for instance, that tries to reconstruct a manifold from data. Here, the geometric characteristics that are usually taken into account are mostly intrinsic dimension. Classical manifold learning algorithms such as multidimensional scaling and isomap are able to approximate the intrinsic dimension of the data manifold, but are not able to learn the curvature, right? In fact, learning curvature from data is generally very difficult. And in particular, to my knowledge, there's very little work out there on how to do this with non-asymptotic error bound. So our way here, our framework here does, of course, not allow us to capture the whole Riemann tensor of the data manifold, but we can at least learn something about the Ricci curvature, which is one piece of it and one way of characterizing the curvature of data. So in a sense, this kind of characterization that we get from this framework is complementary to the kinds of information that we get from manifold learning. There are, in particular, so thinking now about these global curvature bounds. So there are some really nice results on sampling and also on spectral data analysis methods that have guarantees of efficiency in bounded, for manifolds with bounded Ricci curvature. So being able to certify that a certain data set at a certain manifold falls into that regime is like very valuable from that perspective. We also have in the paper, sort of as a first application or first side note, contraction result in terms of global curvature bounds that gives some insights into where certain types of spectral methods might be expected to work well. So this is one set of applications. And then another set of applications that is very recent work. The geometry of the data manifold also has an impact on the complexity of learning certain architectures such as neural networks. To take a step back, very briefly. So learning or training neural networks with algorithms such as gradient descent is known to be hard, so not efficiently doable. For even simple, shallow feed-forward networks, and even under very simple data distributions, such as Gaussian input sequence. That's been established quite recently in 2 papers by Diakonikolas et al. And Chen et al. Chen here is Sitan Chen from Harvard. And in this line of work, we were interested in understanding what kind of geometric structure might be able to get around this, might remove those fundamental limitations. The first thing that we looked at, just to briefly mention that here, is equivariant neural networks. So those are neural network architectures for learning on symmetric data. Graph neural networks that we've seen earlier would be one example where the domain is permutation invariant. And there we were able to show that just encoding symmetries as an inductive bias in your architectures does not make the network efficiently trainable. So that is not enough, not strong enough of an inductive bias. In more recent work, we took a closer look at the geometry of the data manifold. So are there any geometric properties of the data manifold that remove those limitations that make neural networks efficiently learnable? So the first thing to try here is the manifold hypothesis, right? This was the implicit assumption that we made earlier when we constructed the geometric graph, that our data lies on some low dimensional manifold, even though it might be given in a high dimensional space. And it turns out the manifold hypothesis itself, so this presence of a low dimensional structure, is not enough to guarantee learnability. We can construct pathological instances that are still hard, where neural networks are still hard to learn. It turns out, however, that there are additional geometric restrictions that one can make on the data manifold that make the neural network efficiently learnable. And one of them is bounded Ricci curvature. There are others, so this is not exhaustive, but bounded Ricci curvature. So these global bounds that we just saw that we can learn from the point cloud with Olivier Ricci curvature, this would certify that we're in a setting where the neural network is efficiently learnable. Okay, and with that, I'm out of time and I want to conclude. So in this talk, we discussed discrete notions of curvature on graphs and how to derive them from curvature analogies. We also talked about using curvature or insights from curvature in the context of graph neural networks. We talked about rewiring and encoding to mitigate things like oversmoothing, oversquashing, and also the limited representational power of graph neural networks. And then at the end, we talked about how we can use Olivier's curvature to learn something about the geometry of our data manifold, both in a local and a global sense. And then very briefly on why that might be important for machine learning. Here are the main references that I talked about. And I want to acknowledge my co-authors. So basically all the work that I mentioned related to graph machine learning for curvature, so oversmoothing and oversquashing, encodings. This was Luca Professor, who is a PhD student at Harvard. And then the continuum limits of curvature is joint work with Nicolas Garcia-Trios, who is a faculty at the University of Wisconsin. And then here are some other co-authors of work that I mentioned. And that's all. Thank you.